Hello, and welcome to Group 1's interim presentation for an onboard electric vehicle charging system. Collaborating on this project are John Bellapatrick, Emma Heaton, Ramon Howe, Kayla Singleton, Dylan Tabalon, and Benjamin Yang Jing Yap. The self-charging EV system is designed to capture mechanical energy from all four vehicle wheels while in motion and convert it into electrical energy to trickle charge the battery. The system consists of three main subsystems: wheel-mounted energy capture units, a battery transfer case for energy conversion and storage, and electrical wiring components to deliver power to the res. Key design variables include harvesting schedule, gear ratio, capture torque, transfer efficiency, voltage, and wiring capacity, all constrained by factors such as wheel speed, motor weight, thermal limits, and battery specifications. The subsystems work together by capturing energy at the wheels, converting it in the transfer case, and safely delivering it through the wiring system to recharge the vehicle's battery. While not intended to replace conventional charging stations, this system helps reduce energy consumption and costs for EV owners, while providing additional driving range and enhancing overall vehicle efficiency.
Subsystem 1 is the energy captured at the wheels. This consists of the design variables that are harvesting schedule, gear ratio, and capture torque. The harvesting schedule are what conditions are necessary to extract energy. The gear ratio keeps the generator in its efficient operating band across vehicle speeds, while capture torque is a maximum captured torque per wheel. It's how hard the system loads the wheel to extract energy. Our objective function sought to maximize the power generated from wheel energy capture units. This function consisted of the number of wheels, the wheel rotational speed, wheel diameter, number of motors, generator efficiency, and wheel angular velocity, some of which were constrained by component reliability and safe operating conditions. For our modeling approach, we sought to determine the wheel angular velocity, then calculate the mechanical energy extracted, apply a gear ratio transformation to convert the wheel speed to a generator speed, and then convert the mechanical power to electrical power using the generator efficiency, then multiply by the number of wheels and the harvesting schedule. Below you can see some of the assumptions we made during our modeling. For our optimization method, we use MATLAB with the fmincon function, and this is because our objective function was nonlinear, our constraints were nonlinear, and our design variables were continuous. Additionally, we used a genetic algorithm, which we speak more about in our report. Below are some of our preliminary results for optimization. We found a maximum power output of 2,840 watts, which would then go to the battery subsystem. And we also found that thermal limit was our dominant constraint.
Subsystem 2 focuses on the transfer of energy from the capturing subsystem to the battery subsystem. Parameters include ambient temperature, maximum allowable case temperature, maximum transfer case volume, as well as thermal resistance. Energy transfer efficiency, output voltage, and transfer power are captured as the design variables. Lastly, intermediate variables required for the subsystem are transfer power in watts, resulting current, power loss, transfer case temperature, and transfer case volume. Continuing with the subsystem 2 optimization model, the subsystem is constrained thermally and by the transfer case volume. The objective function of the subsystem is to determine the power transferred to the battery with a low power loss and smaller case volume, enabling higher allowable power delivery. Higher transfer power would lead to higher power loss, higher temperatures, and a larger transfer case volume. The optimal solution exists where transfer power is maximized without exceeding the thermal and transfer case volume constraints. The objective of the modeling approach to subsystem 2 was to capture key trade-offs of transfer power, thermal behavior, and case volume while delivering highest power output to the battery. Key assumptions in our model included keeping ambient temperature, electrical efficiency, and thermal resistance as constant, transfer case size scaled linearly with transfer power, as well as assuming a maximum operating power of 20 kilowatts and maximum operating temperature of 60 degrees C. Major modeling steps were to define the design variables, followed by computing intermediate variables, evaluating constraints, computing the objective function, and finally returning the optimization results.
For subsystem 2, our optimization method was done in MATLAB using fmincon. We defined three design variables and used them to optimize the output power. The main reason we selected fmincon is because our problem is a constraint nonlinear optimization problem. The objective function is nonlinear, the variables are continuous, and there are clear inequality constraints. We also look at simulated annealing as another possible method, but compared to that, fmincon gave us a more efficient optimization process for the subsystem. For the optimization results, the optimal design point, or X star, gives us an energy transfer efficiency of 0.95, an output voltage of 180 volts, and a transfer power of 5 kilowatts. Based on these optimized values, the objective functions results, or F star, show that about 315 watts of power can be delivered to the battery subsystem from the onboard vehicle charger. This means the system should be designed to support 95% efficiency between the energy capture system and the battery, while maintaining an output voltage of 180 volts and a transfer rate of 5 kilowatts. This slide summarizes the main discussion from the optimization results. First, the results show that thermal effects and case size penalties increase faster than the performance gain from higher output power. Second, this means the subsystem is operating in a loss-dominated regime. In other words, reducing inefficiency has a bigger impact than simply trying to increase output power. Finally, overheating risk is the main factor limiting the subsystem output power, so overall thermal management is a key design priority for this subsystem.
Subsystem 3 focuses on the electrical wiring system that transfers energy from the battery transfer case to the rechargeable energy storage system. The main parameter in the model is charging time, assumed to be 1 hour. The design variable is transmitted power. The system must satisfy several constraints, including the use of 00 AWG wiring, an energy capacity between 75 and 100 kilowatt hours, and a wiring bundle diameter between 25 and 50 millimeters. The objective of the subsystem is to maximize the energy transferred to the battery. Energy is calculated as power multiplied by time. Increasing power increases energy delivery and helps extend EV range. However, higher power also increases current and wiring size, which may violate the bundle diameter constraint. We developed a deterministic electrical model that calculates current and bundle diameter based on transmitted power. The model assumes copper 00 AWG wires, constant voltage, and small power losses. The optimization evaluates the constraints and determines the optimal power that maximizes energy delivery while satisfying all system limits.
For the optimization method, we used MATLAB with its FMINCON, or Constraint Optimization Solver. Our approach was to define power as the design variable and apply system constraints. We chose this method because it handles nonlinear constraints, is efficient for engineering design, and allows for multi-start and sensitivity analysis. After we ran our model, these were our optimization results. X star had 3 variables, with optimal power being 80 kilowatts, number of wires being 8, and bundle diameter being 26.21 millimeters. F star had the variable of energy delivered and came out to 80 kilowatt hours. Some keynotes were that optimal power balances energy delivery and wiring limits, bundle diameter constraint becomes active at high power levels, and that the energy constraints were always satisfied within the target range. As a result of the outputs from our model, we optimized the wiring subsystem to efficiently deliver energy while meeting the 2 zero-gauge wiring requirement, 75 to 100 kilowatt hour energy capacity range, and the 25 to 55 millimeter net wire bundle diameter range. This optimization allows for a reliable and efficient energy transfer to extend the EV range.